This video is going to talk about some of the solid design principles. So the single responsibility principle, the open and close principle. We're going to cover dependency injection, and we're going to talk about this in the context of making code more testable and writing better tests. So I'm using as an example as the kind of and when I say testing, I'm referring to kind of unit testing there. And I know there are various conversations around kind of what sort of tests you should write and shouldn't write and all that kind of stuff. But this is starting at the moment on unit testing. So I'm using my starting point for this is a class here, a common thing, which has got a dependency on another class called other thing. And common thing class does lots of different things. Does thing A, thing B, thing C, and thing D. So this is a common thing that I see in code where we have large classes that do lots of different things, and classes that have then dependencies on other things. So big classes with lots of dependencies. So I hope as an example, although it's fairly abstract in terms of its kind of naming and stuff, I hope in terms of the sort of structure, it's identifiable as something, something that you've seen before, and just to kind of highlight, just to allow me to kind of highlight some of the issues through this, the dependency. Other thing, creates database connection and runs queries and stuff like that. So we've got that extra dependency on the external database with all that entails. So my goal here is to write testable code and write unit tests for my code. So we're going to start off just trying to write a unit test for this. So I've still got you can see the change basically between these two files. I've still got my common thing. I've still got my other thing. The only thing that I now have in addition is this test class. So I'm making an assumption here that we've got a test framework in place, a unit testing framework in place, and that we're using that as the basis for our classes. If you're not sure what this kind of refers to when we're referring to a sort of testing framework, then I suggest kind of going and googling unit testing frameworks. But most languages will have a unit testing framework of some description. And as with most common unit testing frameworks, there'll be some form of kind of setup function, there'll be a teardown function, and then you've got your tests that get run within that class. Because we have common thing that does lots of different things, so we've got lots of functions within test common thing to allow us to test that. So there are a number of issues that I have with this. One, we've got this kind of, as well as now having a big class here that's doing lots of different things, we've also got an equally big test class that needs to be big because it's having to go through all the different things that the common thing class does. So it's not ideal that we've got test classes that are big and unwieldy. It's not ideal that we've got our main classes has been kind of big and unwieldy. Equally, the fact that when we try to test common thing, for unit testing, we're trying to isolate the thing that we want to test. And because we have this dependency of common thing on other thing, we are not getting that isolation. When we test common thing, we are testing other thing as well, and we're testing the database. So when we run this test, and we want to see whether it's succeeded, this could fail for many different reasons. It could fail because the functionality in the common thing class is wrong. It could fail because the code in the other thing class is wrong. It could fail because the database is not running or has fallen over. It could be failed because the data in the database has changed. There are so many reasons why this could fail. And from a unit testing perspective, we want to isolate this so that when this fails, it only fails because we've made a mistake in the common thing class. That gives us real useful information whilst we're developing. So you're making a change to the common thing class, you run the test, it fails. You know that you've broken something in that class. If when you run the test and it fails, you don't know why it's failed, it could, there's many different things that could have caused that failure. That's not really helping you with making the changes to the class that you're working on. So you've got to get that isolation. Helps you know you've worked on something, you've changed something, an error was thrown, and the error was thrown because of something that you have done. And to have that confidence, I would suggest is quite an empowering thing from a development perspective. If you get back information that you're uncertain why it's happened, that's not empowering. Particularly if you were to go back and say, look at your code and think, well, actually, I can't see that I've made a mistake there. Maybe it failed because of something else. Even having that doubt, thinking maybe it's not something I've done, maybe it's something else. It's all the wrong things. If we want efficiency in what we're doing, knowing that we make a change, something fails, we know why it's failed. That allows us to kind of work with confidence. So I hope that gives enough of an idea as to why this type of setup with big test classes, big main classes, dependencies, is not a great idea. Equally, the fact that we're actually using the database here, say potentially it could be slow as well. So we're not only going to be getting back data that we're not sure of how correct that data is going to be, but also the test may not run fast enough that we get results in a timely fashion. So I hope that kind of illustrates why there's a challenge to this type of setup. So as another example of kind of issues that arise there, if we add a function to our common thing application, we're now straight away we've lost our code coverage, and we now need to modify the test code in order to add that new thing in there. So we're modifying the common thing, so there's a chance we're going to break common thing, and all these other things are going to start failing. We're modifying the test code, so now there's a chance we're going to break things here as well, and they might start failing. So it's just lots of little things that can trip us up, and we want to try and minimize those. We want to try and minimize the things, minimize the opportunity for us to trip ourselves up effectively. So let me introduce that single responsibility principle. With the single responsibility principle, we're essentially saying that we want our classes to do one thing, to have one responsibility. Common thing is doing lots of things. Thing A does one thing. It has one responsibility. Because thing A only does one thing, our test code can be a lot smaller as well. So straight away we've got less code here, we've got less code here. The relationship between our functional code and our test code is much clearer. We know what we can be clear that this code in our test class is testing this, whereas in our the common one we've got a lot of test code, we've got a lot of main code, and it's not really kind of clear. Well, could these things, what's testing what? How's that working? Lots of reasons why it just becomes unreadable and not particularly useful. Obviously, if we're we've created a class for thing A and a test class for thing A. We will now need to do that. If we break this common thing out into multiple classes, we're going to have multiple instances of this, or so multiple classes for thing B, C, D, and E, and we're going to have test classes as well for sort of covering those. But the fact they're separated out, when we want to work on thing A, we can work on that and its test in isolation, knowing that we've found those things and isolated them. So I hope just seeing that smaller set of code, both in the main class and in the test class, is some evidence that that splitting things out into separate things so that things only have one responsibility gives us one aspect of what we need. It makes things more readable. So the next thing. The next thing, if we now, so we're having now got our thing A that's nice and small, single responsibility. If we want to now enhance that function and give it a related but kind of better function, one way we can do that is to add this new function into class thing A. It does this. It's got this enhanced functionality. It's not just getting stuff; it's now getting better stuff. That's good, right? Get better stuff. It's getting more stuff. It's a good thing. So we're enhancing this stuff, and we've enhanced thing A. Having now added that new functionality there, we now also need to edit our tests. So again, we've got slightly again undesirable situation where in adding new functionality to our main code, there's a risk we can break the main code, and there's also a risk that we could break the test code as well. So that's not ideal. An alternative to adding this new functionality into thing A is to use inheritance. So rather than adding the new functionality to thing A, we can extend thing A, create a new class that extends thing A, and put our new functionality in there. From a testing perspective, that means we can then create a new class that relates to the new functionality, that tests that new functionality. And so we've now got one test class that matches to our original class. We've got a new test class that matches to our new enhanced class. That means that our existing we've not had to change our original class. That remains exactly as it is. So we can guarantee we've not introduced problems there, and equally our original test class hasn't changed. So we can guarantee we've not introduced new problems there. And instead, what we've got is an enhanced class and a new test class to go with that. So we've got some additional things that represent that new functionality. And so this is the O in solid. This is the open and close principle. And the idea being that thing A should be open for extension but closed for modification. So we've not modified this. This is stayed exactly the same, but we have extended it. Now there are some there are some subtleties to this. This is not a hard kind of concrete rule. The idea that something should be closed for modification relies on the idea that something can have a state of being complete. That a class can have a state of being complete, where it fulfills the responsibility that it was originally meant to have. That was that. It does that. It does all of those things, and it is now complete and needs no further functionality adding to satisfy that responsibility. If we think back to our common class, for example, the mere fact that it's a common class suggests we're going to keep on adding things to this. So we can say that this common class is unlikely to have ever have a status of being complete, because we're just going to use it as a dumping ground to put stuff into. Whereas if we have something with a single responsibility, there is a much greater chance that we will be able to define a complete state for that thing and say, right, there was a requirement for a class. This class fulfills that requirement and it is now complete and needs no further work. That means that if you then have a new requirement, you're effectively defining a new responsibility, and that is deserving of a new class. You may extend thing A in order to because it may be kind of related, but we're effectively saying this is a new requirement, so we're creating a new responsibility there. So there is a it is dependent on that idea of something having a complete status. Equally, you might go through multiple iterations of the design of a class in order to get to that complete status. So whilst you're going through those designs of that class to get to its complete status, you are modifying it. So the open-close principle is not saying that every modification that you make to a class should be an extension. So you should basically be inheriting every single time you make a modification. That's not the intention. It's the idea that when you have an idea for a class, that there is you design that class, there is a point at which you can say this is complete. It needs no more functionality to be complete. This is it. At that point, if you have effective test coverage, that class and those tests work together, need never be modified again, and should always continue to work. And effectively then, any modifications you do make to that are it's just a risk that you will then break something else. So the less modification work you need to do, the more stable you can make that code. We are, after all, human beings. We make mistakes. So the less things we do, the less chance there is of us making a mistake. Put simply. The one exception to that modification would be if you find a bug. If when creating the class thing A, 6 months down the line, you find a bug in the code, then you should modify the code in order to resolve that bug, because you would not create a new class extending the original one in order to fix a bug. If there's a bug in the code, then it is not fulfilling its complete status effectively. That would be a justification for modifying the code to resolve that bug within the original class. Another example that I was asked about was, what if you create a class based on an original requirement and then later on that requirement changes? Should we then modify that original class? And I would say then, the answer is no, because that class which you created to meet that requirement may be used in multiple places, and the requirement that has changed may be a requirement in only one of those places. So you should create a new class. It may be a completely separate class. It maybe extends the first class. That depends on the the nature of the change to the requirements. And then in the place where the code was using the original class, you would then change to use the new class. So that would mean that places where the requirements has changed, it can use the new functionality. Places where the old requirement may still be the valid one, can continue to use that one. So if a class was created to fulfill a requirement, and the requirement changes, chances are that's going to be a new class. So that's the open and close principle. That gives us the ability to keep our code stable, whilst also offering a means to enhance that code further. You notice what we still have in here is the dependency. We still have, our thing A is still dependent on other things. So when we come down to our tests, we're still testing other thing at the same time as testing thing A. So now we move on to dependency injection. So previously, when the constructor for thing A was called, it created an instance of other thing, a new instance of other thing. So let's just turn that there. So in order to modify that so that we are no longer creating our own dependency, we change it so the constructor takes an argument of other thing. So that's passed into it. So that's a modification to the constructor, and we're now no longer creating our own dependencies. That means that in our test code, we can create that dependency. So we've created the other thing here, and we're now passing that into thing A. So thing A is now kind of it's no longer creating that dependency. Something else is creating the dependency. And you may well ask, well, how is that going to help? How does that help anything? And we will find out. So we're still here. We're still dependent. Even though our test code has created other thing, we're still testing. We're still testing other thing. We're still passing it into thing A, and we've still got all the same problems. We've just restructured things a little bit. So what ideally we want to be able to do here is bring in a test class and say, actually, we don't want to test other thing and the database and all that kind of stuff. We just want to be able to have a much simpler class that effectively isn't being put into test here. So what I've done is I've defined a new test class called test other thing. So we've got other thing, we've got test other thing. Test other thing implements the same method of get stuff, but it has no constructor because it doesn't do anything in its setup phase, and it doesn't perform a database query. Instead, it just returns some text. So we can guarantee every time that gets called, it will do the same thing. It will always do the same thing. That's where we want to be. So now it tells me that I'm missing out these braces. So yeah, we've now got a test class, implements the same method, always returns the same thing. From a testing point of view, that's great. We want it to always return the same thing. And because we don't have this database connection, it's going to be a lot faster, and we're also not dependent on things like the database being up and all that kind of stuff. So that's a good situation to be in. So we come down to our test code, and we now say, right, rather than other thing being an instance of other thing, it's now an instance of test other thing. Implements the same method, and we'll now pass our instance of test other thing into thing A, but we've got a problem because that's going to fail. It's going to fail because thing A is dependent on the other thing class. It's not dependent on test other thing class. So that's the next problem that we need to overcome. And this is where interfaces come in. So an interface is a contract. It's a contract that a class that implements an interface is promising that they will implement the methods defined in that interface. That then means that any other class that needs to call a method on an object, if it's rather than defining a dependency on a particular class, if it defines a dependency on the interface, then it can call the method defined in the interface with confidence, knowing that any object that gets passed to it will implement that method. It's just a massively important aspect of programming, and I think in terms of both interfaces here and in terms of APIs, that idea of the contract is something which is poorly understood. You know, it's this two sides to a contract. One is providing something to someone else, and that contract defines, you know, what this party is going to provide, and this party can then rely on the fact that it will get those things because there is a contract defining that thing that it's going to get. So in this instance, we've got two things that are agreeing to implement the stuffable interface. So I should say we've got an interface here which I've called stuffable, and the stuffable interface just defines one method, which is get stuffed. So it get stuff, and I've then got the two classes, the real class and the test class, that are implementing that interface, and I've got thing A, which is now dependent on something of that, you know, using that interface. By implementing the stuffable interface, other thing is promising to implement this get stuff method. Likewise, test other thing by implementing the stuffable is also promising to implement the get stuff method. By making thing A dependent on stuffable, it can then call the get stuff method on this object, knowing that it will get executed because the argument that gets put, the value that gets passed in, the object that gets passed in, will implement that method. If I try to call a method on this object that, say, doesn't exist in the interface, get stuff 2, I will get a compiler error because there's nothing that tells the compiler that this method that thing A is trying to call on the object that's being passed in. There's nothing that tells it that get stuff 2 method is even going to exist. So the compiler needs to know that the methods that are being called on objects do exist, and having the interface there tells the compiler that they exist. So if I now come down to our test code, our other thing is an instance of test other thing, and we can now pass that value, that object, into thing A, and this will succeed because test other thing implements the stuffable interface, and thing A is dependent on the stuffable interface, and therefore everything is well with the world. If I was to take out that implement stuffable and just leave it like that, so we've got we have no interface there, we could not pass that in because it's not guaranteeing to implement the stuffable interface. It's only through having that implement stuffable line there, that thing A will accept it because this promise exists. I will implement the stuffable interface. Equally, if we were to take out the implement stuffable from the real other thing class, that could no longer be used with the code as defined, because again, it's no longer. This is now dependent on something which promises to fulfill that. If we take that out, it's no longer promising to fulfill that. So in the real code, in the production environment where the other thing class is being used rather than test other thing, it would fail unless we have that implement stuffable. From a testing point of view, what this means is we've completely broken that dependency on other thing, which means we can delete. If we wanted to, we could just delete that code completely. So we've now got an interface. We've got the class that we wanted to test. We've got the test class that just does something very, very simple and isn't really going to affect the testing of our code up here. And we've then got our test code itself, which is running those tests. So this is an ideal. This is we're almost there. We're almost there in terms of getting where we want to be. We've got a reasonable amount of code that's doing a well-defined thing. We're not dependent on other objects. At least to return. We're not dependent on other classes. And we're actually injecting our dependencies into the code we want to test, and the thing that we inject in is doing something predictable. So that's an ideal scenario. Let's put that code back in there. But there is still an issue, and that's so test other thing is guaranteed to return this, which is great because that's what we wanted here. But what happens if we want to test other things? What happens if we want to test if the response from get stuff is not good? What if we want to test errors? So one solution to that, as we can see here, I've created another test class called test other thing error, and rather than returning thing we want A, returns an error code. And we can now create functions in here, separate functions, one to do the original thing, and one to do the testing the errors. So we're creating an instance of test other thing here, passing that in, running it, testing that we get the successful stuff back, running test other thing error, or creating an instance of test other thing error, passing that in, running it, asserting that what we get back is an error of code 1. We've managed to kind of cover all of the bases there, but it's less than ideal because we're now having to write these, test classes for the dependency, and if we want this test class to do different things and exhibit different behaviors so that we can test how thing A reacts, we're just going to end up with loads and loads of test code in there, which is, again, less than ideal. It's not what we want. We want to try and keep this to a minimum. And thankfully, other people also thought that would be a good idea. So the idea of the mocking framework was created. And the mocking framework allows you to say, I need, in order to satisfy thing A's requirements for something to go in here, you can say to the mocking framework, give me an object that conforms to this interface so that I can pass that into thing A. And it will do that. And you can tell that object, that mock object, this is how I want you to behave. So in the example here, we're telling test other thing, it's going to behave like this and return this good code. And we're telling test other thing error to behave like this and return an error code. So in a similar way, with mock objects, you can you can tell them how they should behave, but it's just in a much lighter, much more sustainable manner. So here we have our kind of last example. So have our interface, we have our original class. We can get rid of the other thing class. We don't need that anymore. We have our test code. We've set up our test as per usual. We have our function do thing A, and we've got our function test do thing A error. So we're still testing the successful situation. We're testing the error situation. But what we're saying is that rather than other thing being an instance of a test object, we're now going to call a mocking framework. And again, most languages will have the unit test framework. They will also have mocking frameworks, and the mocking framework and the unit test framework will normally, work together well. So in this instance, we're creating we're asking the mocking framework to give us an object that conforms to the stuffable interface. So that will return an object back that conforms to the stuffable interface. That then allows us to do some really quite clever things. So we're going to inject that object into thing A as we did before, but rather than just injecting it in, we're going to at the same time, we could do this separately, but I'm just doing it at the same time. We're going to be setting up some properties of that other thing object. So it would normally work. The mocking frameworks normally have some sort of syntax like this. So I've just kind of almost made this up as a sort of a pseudocode example, but they all have something similar to this. So you can describe what you want to happen in a line of code on the mock object. So what I've said here is that this other thing mock object that conforms to the stuffable interface expects get stuff to be called. So that effectively means that we're saying that that function should be called, and that when it gets called, it should return this value here. So then when we call that, we can assert that we've got the right thing. We could also have an assertion in there that actually that what we expected to happen, you might have something around asserting the expectations of the mock object were met, or that kind of thing. So that way, if you called thing a.do and it didn't call get stuff, this expectation would fail because we've told it this should be getting called and it should be returning that. So if it doesn't get called, that's an issue. That's a problem. So the mocking framework can allow us to describe that behavior. Equally, down with that error, we can tell it that we want it to describe a slightly different behavior. So we're still describing that we want the get stuff method to be called, but we're saying that it's going to return an error this time. And again, we can then assert that the error happened. So now we've got to our utopian situation where we have a class. We've got a class that's under test, and we've got a test class, and we've got our test code, and that's it. We've got our interface defined up here. That's kind of nice and simple. But essentially, we've got no other code. So the dependency code that we had originally, way back with things here, that code which we had to have here to enable all this stuff to run, we don't need that anymore. That's gone. So we don't care about that. All we care about is the thing we want to test and the code that we're actually using to run the test. We've got a nice simple class here, so it's nice and readable. We've got a nice simple bit of test code that's nice and readable. It's doing some nice simple tests, checking that things that work successfully, and if they're things that are erroring. If we had completed the design for this and we'd implemented all the functionality we need, we could say this is now complete, and we could then kind of commit to any further changes to, or any further work we wanted to enhance the functionality around this would be an extension, which means this code will never change. This code will never change. So we've got a stable code base there. The only reasons we're going to change this code are either if we find bugs. Well, yeah, if we find bugs in thing A, and that will likely, if we've got bugs in thing A, then chances are we're going to need to write new functions in the test code to capture those issues, and then we're going to modify thing A to pass those. We're going to write tests that highlight the issue that fail, and then we're going to write code in here that then allows that test to pass. We've injected we've made it so that our original class thing A accepts a object passed into it rather than creating it itself. So we've broken that dependency there. We have made it dependent on an interface rather than a class, which means that we can now pass different objects of different classes into here as long as they conform to the same interface, which allows us to then control the behavior of that object. And then in order to give us flexibility and simplicity around defining that behavior, we are using a mocking framework. And the mocking framework creates an object that conforms to an interface, fulfills that contract, and we're then using that object to describe behavior that we expect to happen on that object and how it should behave. We're passing that into thing A. Thing A can then execute its methods, and we can test the results. So, that is where we want to. That's where we want to be. We started here with big common classes that it's not clear what their purpose is, dependencies on other classes, and no test coverage. And we've worked through to the point where we have classes that are smaller, better defined, clearer in their purpose, without dependencies, and with test coverage, without the need to write kind of big complex tests. And if we commit to not modifying this once the design has been completed, then we should have a stable, sustainable code base with a set of tests that don't need updating unless there are bugs. It's not everything. It's not everything. Unit testing will not cover everything, but it is a good stable base to work from. There are many aspects to testing, but this is a foundation element to a testing strategy. So I hope this has been helpful. If you've got any comments, feel free to feed them back. Any requests, also feed them back as well. Thank you very much.